Section 5.5, we're going to look at solving rational equations using algebraic methods, some more, but these equations might have different forms from the ones we saw in some previous sections, like, this one down here as we're seeing. So we're going to determine the least common denominator if there are two or more rational expressions. We're going to solve by using an algebraic approach, and we might solve some formulas for specified variables as well. Okay, so this situation has an interesting setup. We get to do most of the setup ourselves, and we want to think about how this works. So first things first, in our situation here, we have a building and it has 3 exits. 2 are single doors, but they're different sizes. And so the first door by itself can be used to empty the auditorium in 10 minutes. Then the second exit can be used to empty the auditorium in 8 minutes. And the third is a wide door that can open by itself and empty the auditorium in 5 minutes. So if only the first door is open, what fraction of the auditorium can be emptied in 5 minutes? So it takes 10 minutes to empty the whole thing. So in 5 minutes, you could empty a half of the auditorium, right? Since you can do the whole thing in 10 minutes, in 5 minutes, you should be able to do a half of it. And then in 2 minutes, okay, so in 2 minutes, 2 out of 10 would be a fifth. You could empty a fifth of it in 2 minutes. And 1 minute, you could empty a tenth, okay? So a tenth of the auditorium in 1 minute. So the rate at which the door can be used to empty the auditorium is a fraction of the job that can be completed in 1 minute. All right, so we want to determine the rate of emptying for each of these. So the rate that we can empty in 1 minute for the first door is 1/10, right? And then we've already established that, like I said in the previous example, because there were 10 minutes to empty the entire thing, so we can do, it has a rate of emptying of 1/10. 1/10 of it can be done in 1 minute. Now the second auditorium can do the whole thing in 8 minutes, so it should be able to do 1/8 of the auditorium in a single minute. And then the third was the whole thing in 5 minutes, so it should be able to do 1/5 of the auditorium in 1 minute. So what we want to do is to find the time it takes to empty the full auditorium if all of the doors are empty. So this equation right here is we're going to have our first rate, like door 1 is open, plus our second rate, door 2 is open, plus our third rate, door 3 is open, equals 1 over the total time when all 3 doors are open. And that total time is going to be the thing that we want to solve for. So we're first going to write our equation down. So we have our first door open at 1/10, plus our second door open at 1/8, plus our third door open at 1/5 as its rate. And our goal is to find the total time it takes to empty the auditorium if all doors are open. What's the rate for that auditorium? All right, so we're going to first solve this graphically. So I got to get my equation entered. 1/10 plus 1/8 plus 1/5 equals 1 over t. Now, that's not going to graph. So if I want to solve this graphically, I want to graph the left-hand side and the right-hand side separately. So the left-hand side, that's just a number. So we'll graph y equals that number. And the right-hand side, we'll graph y equals 1 over t. Oops, that was supposed to be a 1. Okay, so we've graphed things like this before. So we'll just make ourselves a quick note that if we're going to solve this graphically, we're going to y equals both sides. And as you can see, that's the only way to enter this thing because it's not going to show up otherwise. All right, so I can see my intersection point right here. And so it's going to take 2.353 minutes. Okay, so t equals 2.353. So it takes 2.353 minutes to empty the room. Now, I knew it was going to be less than 5 minutes, right? Because I already knew that if just one of the doors was open, if just the big door was open, the whole thing could be emptied in 5 minutes. And it makes sense that it's around 2.35 minutes because the other two doors were a bit slower, so it's not going to cut the time all the way down to 1 minute or something like that, but it's a little under half of the 5-minute rate. Now, I also want to note that it is not okay to say 2 minutes and 35 seconds because there are not 100 seconds in a minute. If you did want to know how many seconds there were, you could take the 0.353, which is the partial minute, and you could multiply it by 60 since there are 60 seconds in a minute, and you could say 2 minutes and 21.18 seconds if you were in the mood of talking minutes and seconds. But don't say 2 minutes and 35 seconds. That's not true. 2.35 minutes is about 2 minutes and 21.18 seconds. All right. Okay, so then we've solved this graphically. We need to go back and solve it algebraically. All right, so there's an example up above for a similar question, but we've already worked on this in the last section using the general method or the least common denominator method. So I want the least common denominator for all of my fractions. Now, because these have a bunch of numbers, I can do the least common denominator of these fractions and stick a t on it for the fraction with the t in it. So out of 8, 10, and 40, I know that those will all go into, I think I said 8, 10, and 5. I meant to say 8 and 5. I'll go into 40. Sometimes the answer pops out of my mouth before I'm ready to say it. But those numbers, 8, 10, and 5, all go into 40. So my least common denominator is going to be 40t. All right, so I'm going to write down my equation. I'm going to multiply both sides by 40t. So 1 over 10 plus 1 over 8. I'm spacing this out quite a bit. Plus 1 over 5 equals 1 over t. I want to multiply everything by 40t. So times 40t. And again, I want to multiply this whole side by 40t. But if I put this in parentheses, I know this is going to have to distribute. So I'm actually multiplying every single piece by 40t. So I'm just going to write them in so that I can cancel the part of it out. And so the denominator of 10 goes into 40 4 times. So I'm going to left with 4 times 1 is 4t. Then denominator 8 goes into 40 5 times. So I have 5 times t times 1, so plus 5t. Oh, I'm already doing step 2, multiply each side with the common denominator. So cool, we're doing that. And then 5 goes into 48 times, so that's 8 times t times 1, or 8t. And then last, the t's cancel, and I have 1 times 40 is 40. So that's the result so far, but we're going to keep going and get our like terms together. So we've got 5 plus 4, that's 9, plus 8, that's 17t equals 40, and I can divide both sides by 17 and get that t is equal to 2.3529 or 2.353, which is what we said from the graph. Our graph gave us the answer 2.353, and algebraically we get 2.353 if we're going to round it to 3 places. So it takes 2.353 minutes to empty. And how does this equation match what we got graphically? It's the same, thank goodness. So we have a confirmation that our answer was correct. Okay, so the rest of the questions are actually pretty similar to that one. Let's get these set up. So we have, in the next situation, a dome stadium with 2 ventilation fans. The first fan can exchange the air of the stadium in 4 hours. And building code requires a complete exchange of air every 3 hours. So it's really similar to the previous situation with the doors, except that there's not 3 doors or 3 fans. There's just 2 fans going to combine up to the total exchange rate. Okay. So a little more information about this one is we're going to let X represent the change for the second ventilation fan, and we're going to write our equation. So I don't know the 2 fans right here. I know one of my fans. I know the first fan, right? And the other thing I know is the complete exchange. so I know the rate for the complete exchange. So I'm going to start with 1 over 4 plus 1 over x equals 1 over 3. Okay, and we're going to solve this equation graphically. So we know that when we do this graphically, we do y equals the left-hand side, and we do y equals the right-hand side, and then we intersect. So I'll start with y equals 1/4 plus 1 over x, and y equals 1/3. I don't think I can see that intersection point. I love how the dot will pop up, so I'll know where it's at. If it's there, and if it's not there, I'll have to zoom out further. So I can see my dot of intersection there, 12. So if I graph this, they're crossing right there at 12, comma a third. Okay, so my solution is that fan number 2 needs to exchange the air every 12 hours. Okay, it needs an exchange rate of 12. Sorry, Desmond was in the way. Fan number 2 needs to exchange the air every 12 hours. Okay, so the same thing algebraically by multiplying both sides by the common denominator. So 1 over 4 plus 1 over x equals 1 over 3. First of all, what is the common denominator? 4 and 3 both go into 12, and I need an x, right? 4, 3, and x. 12 is the product of 4 and 3. It's the smallest number that both 4 and 3 go into, and then times x. So multiply everything by 12x. All right. Now, 4 goes into 12 3 times, so that's 3x times 1 is 3x. X goes into x once, so that's 12 times 1 is 12. 3 goes into 12 4 times, so that's 4x times 1 is 4x. All right, those are like terms, so we're going to subtract the 3x from both sides, and see, 12 is equal to x. So our answer is match. Takes 12 hours for the second fan. So basically, you don't need a very good fan, number 2. If you already have a pretty good fan, number 1, and you want your exchange to run over 3 hours, you don't need a 1 over 12 fan. So you can buy a cheap fan, I guess, for the second one. That's what the building contractor wants to know. Okay. Now, switching to different fans, suppose that the first fan can exchange air in the stadium twice as fast as the second fan. If x represents the exchange time for the first fan, write an expression that represents the exchange time for the second fan. So the first fan can exchange the air twice as fast as the second. So if our first fan is x, then the second fan is going to be 2x. If my first fan can do it in 3 hours, the second one takes 6 hours, and so on. So it's a little bit slower. So it's going to be twice the speed. It's going to take twice as long. Okay, so 2x. Working together, the two fans can exchange the air in this stadium in 4 hours. So their total together is 4 hours. And so we'll have our 1 over x plus our 1 over 2x equals our 1 over 4 for their exchange rate together. Solve algebraically. And I'm at the bottom of the page. So let me see if I can get this to move up a little bit. Okay. So 1 over x plus 1 over 2x equals 1 over 4. Common denominator on this one. Since I know that 2 already goes into 4, I don't need 8 because 4 is a big enough number to fit both 2 and 4 into it. And x, I just need a single x because x fits into x. So the smallest amount that contains enough for everything is going to be 4x. We're going to multiply everything by 4x. You just need enough that you can completely cancel out every single denominator. So in the first denominator, the x's cancel, so I have 4 times 1 is 4, plus 2 goes into 4 twice, and the x's cancel, so 2 times 1 is 2, equals, the 4's cancel, and x times 1 is 1x. So that would be 6 equals x. Okay, so that means that the first fan can exchange the air in 6 hours? If I'm right, they're going to answer the second fan on the next page. Yep, determine the rate for each fan. Just remember that fan 1 was x, fan 2 was 2x. So the first fan exchanges the air in 6 hours, and the second fan exchanges the air in 2 times x, or 12 hours. And together, a 6-hour fan and a 12-hour fan exchanged all the air in just 4 hours. They were able to cut that down from 6 to 4 by the addition of the second fan. Okay, so again, those 3 questions were all really similar, talking about how those items collaborated, those doors or those fans collaborated, they worked together to combine to that rate, that total rate. Okay, so in the bottom of this page, we're going to look at solving a formula for a specified letter. So first of all, we're going to use this fan situation, and we're going to put some numbers in. So T1 and T2 are exchange rate for some fans working alone, and T is the exchange rate for the total. Determine capital T if T1 is 4 and T2 is 12. All right, so we'll have, in this case, 1 over 4 plus 1 over 12 equals 1 over our total. 4 already goes into 12, so that's going to mean that our least common denominator is going to be 12t. So I can take 12t times each of these. This process is very similar to what we have done before. 4 goes into 12 3 times, so I have 3 times 1 is 3t. 12 goes into 12 once, 1 times t is 1t. T goes into t once, 12 times 1 is 12. So 4t equals 12, and if I divide both sides by 4, I get t equals 3. Okay, so it takes 3 hours to exchange the air working together. All right, repeat using this formula for capital T. Instead of 1 over T1 plus 1 over T2 equals 1 over T, use T equals T2 times T1 plus T2 over T2 plus T1. So T1 is 4 times 12 over 12 plus 4. That's just a number already. So I'm going to go ahead and put that number into Desmos. I'm going to do 4 times, oops, I had to click. 4 times 12 over 12 plus 4, I get 3. Okay, compare the results. I'm already comparing them. My results are the same. And then, I mean, which of these equations was easier to use? I mean, the bottom one was easier to use. I just could type stuff in and get it, versus having to do my common denominator process on this one. The problem comes as, where did this formula come from, right? We got this new formula, it's easier to use, but where does it come from? So the answer to that, this is the same formula, but instead of the little subscripts T1, T2, which get confusing when you're solving, I gotta move decimals out of the way, solving for something, we have just renamed them P, Q, and F, so just different names for the same thing. And we're gonna solve for F. That's where capital T was. We want to get it by itself. So the common denominator here, since those are all different pieces, we're gonna need a P, we're gonna need a Q, and we're gonna need an F. If they had anything in common, then I could have some overlap, but no overlap. So 1 over P plus 1 over Q equals 1 over F. And I need to multiply everything by PQF. All right, so the first piece has P's in common. So then I'm going to have QF times 1. That's QF. Then I can cancel out Q, and we'll have plus PF. Then I can cancel f and we'll have PQ. Now I'm trying to get f by itself. So these two terms both have an f, so I can factor that f out. It's a greatest common factor of those two, and that'll leave me with q plus p equals pq, and then I can divide that off to get f by itself. So divide by q plus p. So this gives me f equals pq over q plus p. And that's where that T2, T1 over T2 plus T1 formula comes from. But it's still a lot of work to do the computation, maybe even more work without the numbers in there. So there's the pro-con of whether you want to solve it in general to get the variable you're looking for by itself, or if you want to plug the numbers in first. So I think I would usually use method 1 to get the numbers in, but you've got some options.